There are 5 lights traveling with 3i Atlas. 5. Not 4, not 6. They maintain perfect formation around this visitor from another star, holding their positions night after night as amateur astronomers watch in growing disbelief. Background stars don't behave this way. Dust clouds don't arrange themselves in symmetric rings. Cometary jets don't station keep. So what exactly are we looking at? Scientists are scrambling for explanations, while online forums buzz with words like Escort and companion swarm. Natural phenomenon? Processing artifact? Or something that shouldn't be there at all? Stay with me through this investigation, because by the end, you'll understand why some researchers aren't sleeping well tonight, and why 3i Atlas might be carrying passengers. Picture this. You're scrolling through your astronomy feed late at night when you see it. Someone has posted an image of 3i Atlas, the interstellar visitor that's been haunting our inner solar system since its discovery. But something is profoundly wrong with this picture. Around the comet's nucleus, arranged in what looks like a deliberate ring, are 5 bright points of light. They're not random. They're not scattered. They're positioned like sentinels, like an honor guard, like something is watching over this ancient traveler from beyond our sun. The images started appearing in early 2025, uploaded by amateur astrophotographers who'd been tracking 3i Atlas as it moved through the constellation of Auriga. These weren't professionals with billion-dollar budgets. These were people in their backyards, their rooftops, their small observatories, using equipment you could buy online if you saved up for a few months. They'd been taking multiple exposures of the comet, some in color, some unfiltered, carefully aligning each frame on the moving nucleus rather than the background stars. This alignment technique is standard practice when you're photographing something that's racing across the sky at interstellar speeds. You want the comet sharp, even if the stars blur into trails. Then came the processing. Astrophotography isn't just point and shoot. The raw images are faint, noisy, filled with artifacts from light pollution and atmospheric interference. So these photographers did what they always do. They stacked their frames, averaging out the noise, then applied sharpening techniques. Wavelet sharpening, unsharp masks, contrast enhancement. These are the tools that bring out the faint details hiding in the darkness. And when they did this to their 3i Atlas images, the 5 points appeared. What makes this pattern so profoundly unsettling is its persistence. These aren't transient flashes or cosmic ray hits or hot pixels on a camera sensor. The 5 points show up frame after frame, night after night, maintaining their relative positions around the nucleus. The geometry appears roughly symmetric, like someone arranged them with intention. They don't drift. They don't scatter. They maintain formation as 3i Atlas hurtles through space at over 40 kilometers per second. The photographers did what any good scientist would do. They checked the background stars. Could these 5 points just be unrelated stars that happen to line up with the comet at this exact moment? The statistical odds of that are astronomical, but stranger coincidences have happened in the cosmos. They compared their images to star catalogs, looked for matches in the Gaia database, cross-referenced positions. Nothing. These luminous points do not correspond to any known stellar objects along 3i Atlas's path. Now here's where it gets weirder. The pattern doesn't look like anything we typically see around comets. When a comet gets active, when the sun's heat starts vaporizing its ices and liberating dust, you get a coma. That coma is diffuse, fuzzy, gradually fading as you move away from the nucleus. Sometimes you see jets, bright streamers of material, shooting out from active regions on the surface. But jets are usually asymmetric, chaotic, changing as the nucleus rotates. They don't arrange themselves in symmetric formations. They don't hold position. This pattern around 3i Atlas looks organized in a way that makes your skin crawl. The online astronomy community exploded. Within hours of the first detailed images appearing, the terms started circulating. Escort. Companion swarm. Station keeping. That last phrase is particularly loaded. Station keeping is what spacecraft do when they want to maintain a specific position relative to another object. It requires propulsion, guidance, active control. Comets don't station keep. Dust doesn't station keep. So, why are people using that word? Because when you look at those images, when you see that formation holding together as 3i Atlas screams through the inner solar system, a part of your brain that evolved to recognize patterns, to detect agency, to spot predators in the grass, starts whispering impossible things. But science is built on skepticism, and the scientific community responded with appropriate caution. Within days, papers and preprints started appearing, urging restraint. These could be optical artifacts, they said. Sharpening algorithms can create ghost points, especially when you're pushing the processing hard. The 5-point pattern might be an interference effect from the way the stacking algorithm handles bright point sources. Or maybe they're real physical features, but not separate objects. Maybe they're bright knots in cometary jets, localized regions where dust is concentrated, illuminated by sunlight at just the right angle to appear point-like. So we're left with a tension that runs straight down the middle of this story. On one side, you have enthusiastic observers saying these images show something genuinely anomalous, something that demands explanation. On the other side, you have cautious scientists pointing out that extraordinary claims require extraordinary evidence, and we're not there yet. Both sides have valid points. Both sides are looking at the same data. But here's the question that should keep you awake tonight. What if the cautious scientists are wrong this time? What if those 5 points aren't artifacts or jets or coincidental stars? What if 3i Atlas, this visitor from interstellar space, this ancient body that formed around another star light years away, really does have companions? What would that mean? Are we witnessing rare comet physics that we've simply never documented before? Some exotic behavior that only reveals itself in interstellar visitors? Or are we looking at something far stranger? Something that challenges our fundamental assumptions about what moves through the space between stars. Let's get technical for a moment, because if we're going to understand what we're really seeing here, we need to understand exactly how these images were made. The amateurs who captured this phenomenon weren't just pointing their telescopes at the sky and hoping for the best. They were using sophisticated techniques that blur the line between amateur and professional astronomy. The typical observation session went like this. Multiple exposures ranging from 30 seconds to several minutes each, taken over the course of hours or even multiple nights. Some photographers used color filters, cycling through red, green, and blue to build up composite images. Others shot unfiltered, capturing every photon they could across the visible spectrum. The key step came during processing. Instead of aligning their stacks on the background stars like you would for most astronomical targets, they aligned everything on the nucleus of 3i Atlas itself. This alignment choice is crucial. When you align on a moving object, you're essentially asking the software to treat that object as stationary and let everything else blur or trail. The stars become streaks, the galaxies smear, but anything that's genuinely associated with the comet, anything that's moving with it through space, stays sharp. So when the 5 points remained crisp and clear after this alignment, it suggested they were sharing the comet's motion. They were traveling together. The sharpening phase is where skeptics raise their eyebrows. Techniques like wavelet sharpening can work miracles on astronomical images, pulling out details that are buried in noise. But they can also create artifacts. An unsharp mask, which is basically a high-pass filter that emphasizes edges, can turn slight brightness variations into apparent discrete sources. Wavelet transforms, which decompose an image into different spatial frequency components, can amplify structures that might not be real. In the wrong hands, or pushed too aggressively, these tools can make you see things that aren't there. But here's what makes the 3i Atlas observations harder to dismiss. Consistency. The 5 points don't just appear in one frame or one observer's data. They show up across multiple independent photographers, using different equipment, different processing workflows, different nights. Yes, they're all using sharpening techniques. Yes, they're all aligning on the nucleus, but they're not coordinating their processing parameters, and they're still seeing the same basic pattern. Then there's the brightness behavior. Several observers noted that the 5 points seem to track the brightness of the nucleus itself. When 3i Atlas brightens slightly after a minor outburst event, the points brighten too. When the comet dimmed as it moved away from the sun, the points dimmed in tandem. This correlation suggests some kind of connection or proximity. If they were background stars, their brightness would be independent of the comet's activity. If they were processing artifacts, you wouldn't necessarily expect them to scale with the nucleus brightness. Another peculiar detail: the points don't blur or smear the way dust typically does. When a comet ejects dust, that material expands rapidly, pushed by solar radiation pressure and the comet's own outgassing. Within hours or days, distinct clumps should disperse, becoming diffuse clouds that blend into the general coma. But these 5 points maintain their definition. They stay relatively compact. They don't fade into the background. Some of the higher quality frames reveal even stranger features. The points aren't perfectly circular. In certain images, they show structure, elongation, almost like they have edges or fins. One photographer described them as having a panel-like quality, though that interpretation might be pushing the data too hard. Others see plume-type features extending from the points, like miniature jets. These details are right at the resolution limit, where the atmosphere's seeing conditions and the telescope's diffraction start to dominate. But if they're real, they suggest these aren't just simple point sources. The nucleus itself looks different in these enhanced frames compared to earlier amateur observations. There are trailing arcs, asymmetric dust structures, bright regions that could be active areas venting material. Some of this is expected. Comets are dynamic, messy objects. But the level of structure visible in these new images is striking, and it raises questions about whether earlier observations simply lacked the resolution to see what was always there. Now for the reality check. No professional telescope has publicly released imagery that definitively confirms 5 separate companion objects orbiting or accompanying 3i Atlas. The major observatories that have pointed their instruments at the comet, including Hubble and several ground-based facilities, haven't published images showing this pattern. That doesn't mean they haven't seen it. It might mean their observations were taken at different times, with different geometries, or that their data processing pipelines don't emphasize the same spatial frequencies as the amateur techniques do. There's also no published astrometric solution that proves the 5 points share the exact motion vector of 3i Atlas. Astrometry is the science of measuring positions and motions of celestial objects. If these companions were truly bound to the comet, moving with it through space, we should be able to track their positions over time and demonstrate that they're following the same trajectory. That analysis hasn't been done publicly, or at least hasn't been shared. Without it, we can't rule out very unlikely coincidences or subtle processing effects that create the illusion of commotion. So, what do we actually know? We know that multiple independent observers, using sound astronomical techniques, are seeing a persistent 5-point pattern around 3i Atlas. We know these points don't match background stars. We know they maintain relative positions across multiple nights. We know they behave in ways that suggest association with the comet. But we don't have the gold standard professional confirmation that would move this from intriguing observation to established fact. Which brings us to the natural question. If we take these observations at face value, if we assume there really is something there, what could possibly explain it? Science progresses by proposing hypotheses and testing them against data. So let's walk through the most conventional explanations for what we're seeing around 3i Atlas, and let's be honest about where they succeed and where they fail. The first idea that comes to mind is the jet knot model. Comets produce jets when sunlight heats localized regions on their surface, causing ices to sublimate rapidly and blast material into space. These jets aren't smooth flows. They're turbulent, chaotic, filled with density variations. Sometimes you get bright knots, concentrated clumps of dust or gas that appear as discrete sources in images. If 3i Atlas has multiple active regions spaced around its nucleus, each producing a jet, you might see multiple bright knots arranged in something like a ring. But here's the problem. Cometary jets rotate with the nucleus. As the comet spins, the jets sweep around like a cosmic lawn sprinkler, and the bright knots move with them. The typical rotation period for a comet nucleus is hours to days. So over multiple nights of observation, you'd expect to see the pattern change, the knots shifting position relative to the nucleus. That's not what observers are reporting with 3i Atlas. The 5 points hold their positions. They don't sweep. They don't rotate away. They stay put. Maybe the nucleus has a very slow rotation. Or maybe we're looking at it pole on, so the rotation isn't apparent? Possible, but unlikely. The odds of catching an interstellar visitor at exactly the right orientation to make its rotating jets look stationary are slim. And even if we were that lucky, the jets themselves would still evolve. They'd brighten and fade as the active regions experienced day and night cycles. They'd change structure as the sun angle changed. Static jet knots over multiple nights don't fit the pattern. Next up, coma shell interference. When a comet experiences an outburst or a period of enhanced activity, it can eject shells of dust that expand outward from the nucleus. If multiple shells are ejected at different times, they can create layered structures in the coma. When you sharpen an image, these layers can produce ring-like brightness features, concentric halos around the nucleus. Could the 5 points be bright spots in such a ring? The challenge here is discreteness. Coma shells are inherently fuzzy. They're made of countless tiny dust particles scattering sunlight, and they fade gradually with distance from the nucleus. Getting 5 discrete bright points from a diffuse shell requires some special geometry, maybe regions where shells intersect or where density peaks happen to align. It's not impossible, but it's contrived. And again, you'd expect these features to evolve noticeably over days as the shells expand and disperse. The reported stability of the 5-point pattern is hard to reconcile with expanding dust shells. Then, there's the possibility that this is all an artifact. Optical and processing artifacts can be surprisingly convincing. Diffraction spikes from bright stars create cross-shaped patterns. Lens flare produces ghost images. Stacking misalignments can create duplicate sources. And aggressive sharpening can turn subtle noise patterns into apparent structures. But generating 5 symmetric points that appear consistently across multiple observers using different equipment? That requires a very specific combination of factors. It's not impossible, but it's rare enough that we can't dismiss the observations purely on artifact grounds without identifying the exact mechanism. What about fragmentation? Comets sometimes break apart, especially when they're stressed by thermal shocks or rotational forces. If 3i Atlas had recently fragmented into several pieces, we might be seeing the individual fragments arranged around the former nucleus. This actually has precedent. Comet Shoemaker-Levy 9 famously broke into more than 20 pieces before it slammed into Jupiter in 1994. Other comets have split into pairs or small groups, but fragmentation for an interstellar object is dynamically weird. 3i Atlas is on a hyperbolic trajectory, moving at high speed relative to the Sun. For fragments to maintain a symmetric formation around the main nucleus, they'd need to be in precise orbits, all with similar periods and orientations. That kind of configuration is fragile. Any slight velocity difference between fragments would cause them to drift apart rapidly at these speeds. Within days or weeks, a fragmented comet should show clear separation, with pieces spreading along the orbit. The reported stability of the 5-point pattern doesn't match typical fragmentation behavior. Could it be background stars after all? The statistical argument against this is strong, but not insurmountable. Space is big. There are a lot of stars. If you look at any random patch of sky long enough, you'll find patterns that look meaningful purely by chance. 5 stars arranged in a rough ring around a moving comet? Incredibly unlikely, but not zero probability. To definitively rule this out, we'd need careful astrometry showing that the points move with the comet rather than staying fixed relative to distant stars. That data hasn't been publicly released. One more natural model worth considering: rotational asymmetry coupled with preferential dust ejection. Imagine a nucleus with an irregular shape, maybe elongated or with multiple lobes. As it rotates, different faces point toward the Sun, and material gets ejected preferentially from specific regions. If the rotation axis and the Sun angle align just right, you might get a situation where dust is continuously fed into specific regions around the nucleus, creating quasi-stable bright areas. This is actually pretty clever, And it doesn't require separate objects. The companions would just be regions of enhanced dust density, continually replenished by ongoing activity. But maintaining a symmetric 5-point pattern this way requires extraordinary fine-tuning. The nucleus would need exactly 5 active regions, spaced almost evenly. The rotation would need to be synchronized with the observation timing. The dust lifetimes would need to be long enough to maintain the pattern, but not so long that it blurs out. It's not physically impossible, but it's asking a lot of coincidences. So here's where we stand. Every natural explanation can account for part of what we're seeing, but none of them cleanly reproduce the full pattern. Jets almost work, but don't explain the stability. Shells almost work, but don't explain the discreteness. Artifacts almost work, but don't explain the consistency. Fragmentation almost work, but don't explain the symmetric arrangement. Background stars almost work, but don't explain the commotion. When every conventional explanation struggles, when you keep finding gaps and problems and awkward coincidences, that's when scientists start entertaining ideas that normally live on the speculative frontier. That's when you start asking whether something genuinely unusual might be happening. What if those 5 points really are separate objects, somehow traveling with 3i Atlas? What if this interstellar visitor brought company? Now we're entering territory where the handrails fall away. These are ideas that push against the boundaries of conventional comet science, but they're still grounded in physics. They're testable. They're falsifiable. They're the kind of hypotheses that might sound wild, but could actually be investigated with the right observations. Consider the idea of formation flight dust clusters. Imagine that when 3i Atlas became active as it approached the Sun, it didn't just eject random dust particles. Instead, through some combination of electrostatic forces, gas drag, and the comet's complex gravity field, the dust self-organized into discrete clumps. These clumps aren't individual objects. They're swarms of countless tiny particles, but they're dense enough and coherent enough to appear as point sources in images. Here's where it gets interesting. Outgassing from a comet can generate torques. As jets fire off from different locations on the nucleus, they create forces that can spin the nucleus up or alter its rotation. But these same forces can affect nearby dust. If you have clumps of dust in the vicinity of an active comet, the pressure from gas and light can push them around. In principle, you could get situations where dust clumps settle into quasi-stable positions, places where the forces balance out. Not true orbits, but more like dynamical equilibrium points. This is speculative, but not crazy. We know that gravitationally interacting systems can have Lagrange points, locations where the combined gravity of two bodies creates stable parking spots for smaller objects. Could something analogous happen with a comet, where outgassing pressure and radiation forces create temporary equilibrium positions? It would require specific conditions, and it wouldn't last forever, but maybe long enough to explain what we're seeing over weeks or months of observation. Then there's the microfragment hypothesis. What if 3i Atlas isn't alone? What if it's actually one member of a small cluster of objects that form together in some distant star system and manage to stay loosely bound during the journey through interstellar space? This sounds exotic, but we know that binary asteroids exist. We know that some comet nuclei are contact binaries, two separate bodies touching or barely separated. Could you have a quintuple system, 5 or 6 objects in a loose gravitational dance? The challenge is that gravitational binding becomes weaker with distance. For 5 objects to maintain a stable configuration around a central body, they'd need to be close enough that mutual gravity matters, but not so close that tidal forces tear the system apart, and they'd need to survive the thermal and dynamical stresses of entering the inner solar system. It's a narrow window, but maybe not impossible for small bodies with low densities and high strength. How would you test this? Long baseline astrometry. If these are separate bodies in orbit, they should show proper motion relative to the nucleus. Their positions should change in predictable ways based on orbital mechanics. If we could track them precisely over weeks, we could determine whether they're following Keplerian orbits or just maintaining fixed angular positions. The former suggests real objects. The latter suggests something else. Brightness curves offer another test. If the 5 points are separate bodies, they might vary in brightness independently of the nucleus, especially if they're rotating or tumbling. If they're dust clumps continuously refreshed by jet activity, they should vary in sync with the nucleus brightness and the jet activity cycles. Careful photometry over time could distinguish these scenarios. Spectroscopy is the ultimate test. Different materials have different spectral signatures. If the 5 points are dusty coma features, their spectra should match the dust and gas in the main coma. Silicates, organics, water ice, maybe some rocky minerals. If they're more compact bodies with different compositions, or if they're somehow less dusty than the surrounding environment, their spectra might differ. A few hours on a large telescope with a spectrograph could answer this definitively. Now let's go even further out. Station-keeping objects. This term makes people uncomfortable because it implies active control. In spaceflight, station-keeping means using thrusters or other propulsion systems to maintain a specific position relative to another object. Obviously, we're not suggesting these are spacecraft. But could there be natural processes that create the appearance of station-keeping? Maybe. If you have objects in the coma that are experiencing balanced forces, radiation pressure pushing out, gravity pulling in, gas drag acting. Tangentially, you might get situations where they hover at specific distances. It wouldn't be true station keeping, but it might look like it over short timescales. The problem is maintaining this balance as conditions change, as the comet's activity level varies, as the distance to the sun changes. It requires a lot of fine-tuning. Some researchers have explored charged phenomena around comets. Dust grains can become electrically charged through photoelectric effects and plasma interactions. Charged grains can interact with each other through electromagnetic forces, potentially creating structures. Could electrostatic repulsion arrange dust into geometric patterns? It's a long shot, but magnetic fields and plasmas do weird things. The comet's ionosphere, the region where solar wind interacts with the outgassing material, is a complex electromagnetic environment. Maybe something exotic is happening there. The key message here is that none of these ideas are confirmed. They're not even mainstream. They're hypotheses, some more plausible than others, offered in the spirit of scientific exploration. The goal isn't to convince you these are true. The goal is to show that there are physically reasonable explanations that don't require abandoning what we know about physics, even if they push the boundaries of what we've seen in comets before. But maybe the way to put this in perspective is to look backward. Have we seen strange things around celestial objects before? Have we been surprised by cosmic visitors in the past? The story of 3I Atlas and its mysterious companions isn't the first time we've encountered something in space that didn't fit our expectations. Cosmic anomalies have a history, and that history teaches us two lessons. Sometimes the weird stuff has mundane explanations, and sometimes it rewrites the textbook. Let's start with Oumuamua, officially designated 1I 2017 U1, the first confirmed interstellar object to pass through our solar system. Discovered in October 2017 by the Pan-STARRS telescope in Hawaii, Oumuamua immediately looked strange. Its light curve, the way its brightness varied over time, suggested an extremely elongated shape, maybe 10 times longer than it was wide. That's unusual, but not unprecedented. Some asteroids are elongated, but then came the acceleration. As Oumuamua swung around the sun and headed back out into interstellar space, astronomers noticed it was moving slightly faster than it should be, based purely on the sun's gravity. Something was giving it a tiny boost. With comets, this kind of non-gravitational acceleration is normal. Outgassing from sublimating ice creates thrust, like a natural rocket engine. But Oumuamua showed no visible coma, no tail, no signs of cometary activity. So what was pushing it? The hypotheses ranged from prosaic to wild. Maybe it was outgassing hydrogen or nitrogen, something that wouldn't produce a visible coma, but would still create thrust. Maybe it had an unusually reflective surface and was getting pushed by solar radiation pressure. Maybe it was a fragment with weird thermal properties. Or maybe, as Harvard astronomer Avi Loeb famously suggested, it was artificial. A light sail, a probe, something manufactured by another civilization. That last idea generated fierce debate. Most scientists found the artificial hypothesis unnecessary, a violation of Occam's razor. If natural explanations could account for the observations, why jump to aliens? But Loeb pointed out that natural explanations required some fine-tuning too. You needed just the right composition, just the right shape, just the right orientation to explain everything. The artifact hypothesis was simple by comparison. It's a sail. We never got resolution. Oumuamua is gone, too far and too faint to observe anymore. But it taught us that interstellar objects can surprise us, and that our intuitions about how cosmic bodies should behave might not apply when those bodies formed around other stars. Then came 2I Borisov in August 2019, the second confirmed interstellar object. Unlike Oumuamua, Borisov looked like a comet. It had a coma, a tail, spectral signatures of outgassing. In many ways, it was reassuringly normal, proof that not every interstellar visitor is weird. But dig deeper and Borisov was strange too. Its composition was surprisingly pristine, with high concentrations of carbon monoxide and unusually low dust-to-gas ratios. It looked like a comet that had never been processed by stellar heating, a frozen relic, preserved since the formation of its parent system. Closer to home, the Rosetta mission to Comet 67P Churyumov-Gerasimenko from 2014 to 2016 revolutionized our understanding of what comets are actually like up close. The images sent back by Rosetta were shocking. The nucleus wasn't a smooth snowball. It was rugged, fractured, covered in cliffs and boulders and dust-covered ice. The jets weren't simple gas flows. They were collimated beams, sometimes erupting from shadowed regions with no obvious connection to sunlight. The coma had structure, fans, and walls, and shells that formed and dissipated on timescales of hours. Rosetta showed us that comets are far more complex than we imagined from ground-based observations. Things that looked like simple fuzzy blobs in telescopes resolved into intricate, dynamic environments when you got close enough. That lesson is relevant here. Maybe what we're seeing around 3I Atlas would make perfect sense if we could send a probe there, if we could resolve it at meter scales instead of kilometer scales. History also includes cases where comets seem to have companions, only for those companions to turn out to be fragments or optical effects. Comet Biela split into two pieces in 1846, and the two fragments were observed separately for several returns before they disintegrated entirely. Comet West broke into four pieces in 1976, putting on a spectacular show before vanishing. These fragmentations were real and dramatic, but they followed predictable patterns. The fragments drifted apart. Their orbits diverged. They didn't maintain formation. There have been suspicious claims, too, observations that hinted at satellite objects or escort structures, but didn't pan out. In the 1800s and early 1900s, before photography and spectroscopy became standard tools, some astronomers reported companion stars or nebulous objects near comets that later observers couldn't confirm. These were likely optical illusions, atmospheric effects, or artifacts of the crude telescopes of the time. The lesson from history is humility. When we see something strange, our first instinct should be skepticism, tempered with curiosity. Most anomalies have prosaic explanations, but not all of them. Sometimes the anomaly is real, and investigating it leads to new science. Oumuamua, whether it was a rock or a sail, forced us to think more carefully about interstellar objects and their properties. Rosetta, by showing us the reality of 67P, taught us that comets are more diverse and complex than our models suggested. So where does 3I Atlas fit in this tradition? Are we documenting the next Oumuamua, a genuine anomaly that will spawn new research and maybe new physics? Or are we in the middle of the next Comet West, watching a natural but unusual fragmentation event play out in real time? Or are we falling for the next 19th century companion comet claim, seeing patterns in noise? We don't know yet. But the fact that we're documenting it, arguing about it, proposing tests and observations, is exactly what science should do when faced with something that doesn't immediately fit. We stay skeptical. We demand evidence. But we also stay curious enough to keep looking. Because if 3I Atlas really does have something unusual going on, if those 5 points turn out to be real and significant, we might be at one of those inflection points where our understanding shifts. Let's talk about what's not being said and why that matters. In the weeks since the 5-point images started circulating, a strange silence has settled over parts of the professional astronomy community. Some of the major observatories that have observed 3i Atlas haven't released their high-resolution images. Some of the professional astronomers who study comets and interstellar objects have been notably quiet on social media. And in certain corners of the internet, people are starting to ask uncomfortable questions about whether data is being withheld. The accusations range from innocent to conspiratorial. On the benign end, some suggest that professional astronomers are simply being cautious, waiting until they have enough data to publish properly before making public statements. Science moves at a different pace than social media. You don't announce a discovery until you're confident it's real, until you've checked and rechecked your work, until you've had it peer-reviewed. By that standard, the silence makes sense. The observations are too new, too ambiguous, too easy to misinterpret. On the other end of the spectrum, some online communities are claiming active suppression. They point to delayed data releases from major observatories, to images that were briefly available and then removed, to amateur photographers who say their high-resolution images were taken down from public platforms or reposted at lower quality. They suggest that someone, somewhere, doesn't want the public to see what's really going on with 3i Atlas. Let's ground this in what we know. NASA did issue a media advisory in March 2025, announcing a live stream event where images from various missions would be shared, including observations of 3i Atlas from Hubble and other assets. This is normal procedure for high-profile astronomical events. Space agencies don't just dump data on the internet. They curate releases, prepare explanatory materials, coordinate with scientists. The live stream hasn't happened yet at the time of this recording, so we don't know what those images will show. What we also know is that professional telescopes have observed 3i Atlas extensively. Hubble has taken images. The Gemini Observatory has pointed its instruments at the comet. Various ground-based facilities have collected spectroscopy and photometry, but not all of that data is public yet. Some is still being processed. Some is proprietary, protected by the observation proposals that secured the telescope time. Some might simply not show the 5-point pattern, either because of observing geometry or because the phenomenon is subtle enough that different processing techniques reveal different things. This is where the methodological divide becomes important. The amateur images that show the 5-point pattern use aggressive sharpening and specific alignment techniques. Professional pipelines might not use those same methods. They might prioritize different aspects of the data, photometric accuracy over fine spatial detail, or spectral resolution over imaging. It's entirely possible that professional telescopes have data that could confirm or refute the amateur observations, but that data hasn't been processed in a way that brings out the relevant features yet. The amateur community, meanwhile, is divided. One camp insists that the pattern is real because it appears consistently across multiple independent observers. If it were just an artifact or a processing glitch, they argue, it wouldn't replicate. Different equipment, different software, different nights, same result. That's the signature of a real phenomenon. The other camp warns that if everyone is using similar processing techniques, stacking on the nucleus, applying wavelet sharpening, they might all be creating the same artifact. Consistency doesn't prove reality if the methodology is biased. Some photographers report that their detailed images have been removed from public forums or that they've been asked to take them down. It's hard to verify these claims without seeing the takedown notices or understanding the context. Were the images removed because they violated platform policies? Because they were copyrighted material posted without permission? Because they contained personally identifiable information? Or because someone actively wanted to suppress them? Without transparency, it's impossible to say. Then, there are the scientific disagreements about what the data actually shows. Multiple teams have published polarimetric observations of 3i Atlas, measurements of how light from the comet is polarized. Polarization tells you about the size, shape, and composition of dust particles. And 3i Atlas shows extreme negative polarization, a curve that's unlike most known comets. Negative polarization means that scattered light becomes less polarized at certain angles, which happens with large, irregular particles or with specific surface textures. This unusual polarization could be relevant. If the 5 bright points are real objects with different dust properties than the main coma, their polarization signatures might differ too. But integrating polarimetry into the Escort hypothesis requires careful modeling, and that work hasn't been done publicly yet. High-profile voices have weighed in with provocative statements. Avi Loeb, the astronomer who proposed that Oumuamua might be artificial, has made comments, suggesting that 3i Atlas could be extraordinary, that the possibility of an artificial origin shouldn't be dismissed out of hand. He's called for more observations, more transparency, more open-minded investigation. Critics accuse him of sensationalizing, of jumping to conclusions without sufficient evidence, of harming the credibility of serious scientific inquiry by invoking alien hypotheses prematurely. But here's the thing. Disagreement is healthy. Science thrives on debate, on people proposing different interpretations and testing them against data. The problem arises when disagreement turns into distrust, when people start suspecting that information is being hidden or manipulated. That's corrosive. It undermines public confidence in science and makes it harder for researchers to do their work without facing accusations of conspiracy. So what would actually resolve this? Transparency would help. If the major observatories that have observed 3i Atlas released their raw data, even without full analysis, the amateur community could examine it. Independent researchers could apply different processing techniques, look for the 5-point pattern, test whether it appears under various methods. Open data fosters trust. It allows replication. It prevents the perception that information is being controlled. Clear communication from professional astronomers would help too. If the pattern is an artifact, explain exactly how the artifact arises. Show us the processing steps that create it. Demonstrate that when you use different methods, it disappears. If the pattern might be real, but requires more investigation, say that. Acknowledge the observations, credit the amateurs who made them, and outline what tests are needed. Science doesn't have to pretend it knows everything immediately. Admitting uncertainty while committing to rigorous investigation is perfectly valid. What we need are coordinated observations designed specifically to test the Escort hypothesis. High-cadence imaging over multiple nights to track whether the 5 points move or hold position. Multi-wavelength observations to see if the pattern appears in infrared, ultraviolet, and visible light the same way. Spectroscopy of the individual points if they're bright enough to resolve. Polarimetry at high spatial resolution to compare the dust properties of the points versus the main coma. These observations are technically feasible. They require telescope time, which is precious, but not absurd amounts. A few nights on a major facility with adaptive optics, a few orbits of Hubble, some coordinated amateur campaigns. If the community decided this was worth investigating seriously, we could have definitive answers within months. But that requires consensus that it's worth investigating, and right now that consensus doesn't exist. Some scientists think this is all noise and artifact, not worth valuable observing time. Others are intrigued but cautious, waiting to see if more data emerges naturally. A few are actively pushing for dedicated observations, arguing that even if the Escort hypothesis is wrong, figuring out why these images look the way they do would teach us something about comets, or image processing, or both. And lurking beneath all of this is a deeper anxiety. What if we don't want the answer? What if part of the scientific community's reluctance to engage with this seriously is because the implications are uncomfortable? If those 5 points are real separate objects traveling with 3i Atlas, it raises questions that don't have easy answers. And if we start seriously considering non-natural explanations, even as remote possibilities to be tested and likely ruled out, we're opening a door that's hard to close. Science is supposed to follow the evidence wherever it leads, but scientists are human. They have reputations to protect, careers to advance, peer pressure to navigate. Proposing a controversial idea can make you a pariah, especially if you're wrong. So sometimes, even good scientists hesitate to investigate things that seem too weird, too speculative, too likely to blow up in their faces. That's where we are with 3i Atlas right now. Caught between intriguing observations that might be real, methodological concerns that might explain everything, professional caution that might be wise or might be excessive, and public speculation that might be justified curiosity or might be conspiracy thinking. It's messy, it's uncomfortable, and it's exactly the kind of situation where careful, open, rigorous science is most important. Because if we get this wrong, if we dismiss something real, or if we endorse something false, the consequences extend beyond this one comet. They affect how we approach the next anomaly and the one after that. They shape whether the public trusts scientists when we say we've found something extraordinary, or when we say we haven't. So what happens next depends on choices being made right now in observatories and universities and space agencies around the world. Will they point their instruments at 3i Atlas with the specific goal of testing these claims? Will they share their data openly? Will they engage with the amateur observations constructively, neither dismissing them reflexively nor accepting them uncritically? Or will this moment pass with the mystery unresolved, the 5 points fading from view as the comet moves on, leaving only speculation and unanswered questions? The clock is ticking on 3i Atlas. Interstellar visitors don't linger. They swing through the inner solar system on their hyperbolic trajectories and vanish back into the darkness between stars, likely never to return. Right now, in late 2025, the comet is still observable, still bright enough for professional telescopes to study. But that window is closing. Within months, it will fade beyond the reach of all but the most powerful instruments. If we want answers about the 5-point formation, we need to act now. The good news is that the observing geometry is improving for some facilities. As 3i Atlas moves along its path, different telescopes gain better viewing angles. The phase angle, the angle between the Sun, the comet, and Earth, changes over time, and certain phase angles can reveal structures that are hidden at others. Maybe in a few weeks, when the geometry shifts, the pattern will become clearer or will disappear entirely, giving us crucial information about what we're seeing. Professional astronomers are planning, or should be planning, several types of observations. High-cadence imaging is the most straightforward. Take pictures of 3i Atlas every night for a week or two, using the same instrument and processing pipeline each time. Track the positions of the 5 points relative to the nucleus and relative to background stars. If they're moving with the comet, their stellar coordinates will change in lockstep with the nucleus. If they're background stars, they'll stay fixed while the comet moves past. If they're artifacts, they might not appear consistently or might change with seeing conditions. Polarimetry is already underway. Several teams have published polarimetric measurements of 3i Atlas showing that unusual negative polarization curve we mentioned earlier. But those measurements were of the entire coma, integrated light from the whole system. What we need is spatially resolved polarimetry, measuring the polarization of the 5 points separately from the main nucleus. If they have different polarization signatures, that tells us they have different dust properties, which would support the idea that they're distinct entities. Spectroscopy is the ultimate tool. Every material has a unique spectral fingerprint based on which wavelengths of light it absorbs and emits. Cometary combs are dominated by water, carbon dioxide, carbon monoxide, cyanogen, and various organic molecules. Dust contributes broad continuum emission from scattered sunlight, plus some silicate features. If the 5 points are just part of the normal coma, their spectra should match. If they're different, compact bodies with unusual compositions, their spectra will differ. Some spectroscopy has already been done. JWST, the James Webb Space Telescope, observed 3i Atlas and found unusually high carbon dioxide emission relative to water. The comet's coma is CO2 dominated, which is rare. Most comets are water dominated, with CO2 as a secondary component. This compositional oddity might be relevant to understanding where 3i Atlas formed, under what conditions, in what kind of parent star system. But JWST's observations were again integrated, looking at the whole system. Targeted spectroscopy of individual points hasn't been published. Ground-based observatories have been busy too. The SWIFT satellite detected hydroxyl emission, a tracer of water, showing that despite the high CO2, there's Still substantial water outgassing happening. Near-infrared spectroscopy from various telescopes has revealed large water ice grains mixed with dust in the coma. These are direct observations of ice particles, not just gas, which tells us about the sublimation process and the size distribution of ejected material. All of this data paints a picture of a complex, active comet with unusual composition and interesting physical properties. But none of it directly addresses the Escort question, because none of it was designed to. The observations were planned before the 5-point images emerged. They're answering different questions about the comet's chemistry and activity level. What we need now are targeted observations specifically focused on the formation. Can we resolve the 5 points individually with adaptive optics on a 10-meter class telescope? Can we track their motion over a baseline of weeks? Can we get spectra good enough to determine if their composition differs from the coma? These are technically challenging observations, but they're not impossible, and we need to consider the implications if the pattern is real. If 3i Atlas really is accompanied by 5 separate objects or coherent structures that maintain formation over the timescale we've been observing, what does that mean for comet science? It would suggest that interstellar comets can bring along small companions, either fragments that broke off during formation or separate bodies that became gravitationally bound. That has implications for how we think about planetary system formation around other stars. If loose clusters of small bodies can survive the journey through interstellar space, maybe such clusters are common. Maybe many interstellar visitors are actually multiple objects flying in formation, and we've just never noticed because we lack the resolution. For planetary science, it raises questions about the stability of small body systems. How long can a few objects remain gravitationally bound while flying through interstellar space? What happens when they encounter a star like our Sun? Do they stay together or disperse? Are there stable configurations, special orbits, or resonances that allow long-term survival? From an astrobiology perspective, the implications get interesting. If interstellar objects regularly travel in clusters, they might exchange material through collisions or near misses. Organic molecules, maybe even microbial life, if we're being extremely speculative, could transfer between bodies. This would provide a mechanism for spreading prebiotic chemistry or even life itself between star systems, a form of panspermia mediated by interstellar caravans. And then there are the mission implications. If we ever want to send a spacecraft to intercept an interstellar object, something like Project Lyra or the various fast flyby mission concepts that have been proposed, knowing that these objects might have companions matters. It changes the mission. Planning. It means you might get bonus science by studying multiple targets during one flyby. Or it might mean navigation hazards you need to account for. But let's be honest. There's one implication everyone is thinking about, even if most scientists won't say it out loud. What if the Escort hypothesis is correct, but the companions aren't natural? What if those 5 points really are maintaining formation through some kind of active control? What if 3i Atlas is carrying probes or instruments or something we don't have a category for? This is where the conversation gets difficult, because even entertaining this possibility opens you up to ridicule. Scientists who suggest non-natural origins for astronomical phenomena are often dismissed as attention-seeking or pseudoscientific, their reputations damaged. But let's think through the scenario rationally, without prejudice. If an advanced civilization wanted to explore other star systems, sending fast-moving objects laden with instruments is a sensible approach. You could equip a natural body like a comet or asteroid with probes that deploy once the object enters a target system. The natural body provides camouflage and raw materials. The probes study the system, looking for planets, biosignatures, signs of technology. It's not so different from how we've proposed using comets or asteroids as spacecraft for human interstellar missions. You wouldn't expect such probes to announce themselves. If their purpose is observation, they'd be designed to be subtle, to blend in. Maybe they'd only become visible when active, when they're maneuvering or transmitting or deploying sensors. And if you saw them from a distance, through a telescope, they might look like bright points arranged in a formation, maybe using reflected sunlight or their own emissions for illumination. This hypothesis is testable. If the 5 points are artificial, they might show non-natural spectral features, unusual brightness variations, or movement that doesn't match gravitational dynamics. They might emit radio signals or exhibit heat signatures inconsistent with passive objects. They might change their formation in response to the local environment or in coordinated ways that suggest communication. None of these smoking guns have been observed. The 5 points, to the extent they're real, look like they could be natural, but we haven't looked carefully enough yet to rule out artificial origins definitively. And given the stakes involved, given that confirming artificial objects in our solar system would be the most important discovery in human history, shouldn't we look as carefully as we possibly can? This is the tension at the center of the 3I Atlas story. Most scientists would say that invoking artificial origins is unnecessary and premature, that we should exhaust natural explanations first. And they're right. Extraordinary claims require extraordinary evidence. But a few voices, Avi Loeb among them, argue that we shouldn't let our discomfort with the implications prevent us from investigating rigorously. That if there's even a tiny chance, we owe it to ourselves and to future generations to find out. So where does this lead? In the next few months, as 3I Atlas moves farther from the sun and fades from view, we'll either get the observations that resolve this mystery, or we won't. We'll either see professional telescopes confirm the 5-point pattern and characterize it, or we'll see the observations fail to replicate it, or we'll see inconclusive results that leave everyone frustrated. And then 3I Atlas will be gone, one more interstellar visitor passing through, leaving behind data, questions, and a reminder of how much we still don't understand about the universe beyond our solar neighborhood. But here's the thing about mysteries. They don't really disappear. They transform. If 3I Atlas leaves without giving us answers, the next interstellar object will arrive eventually. Statistically, we expect to detect a few per year now that our survey telescopes are sensitive enough. Each one is an opportunity to test these ideas, to look for companions, to search for anomalies. And maybe, one day, we'll point our instruments at an interstellar visitor and see something that doesn't fit any natural model. Something that demands we expand our categories and rethink our place in the cosmos. If those 5 lights really are escorting 3I Atlas, if they're maintaining formation as this ancient traveler from another star passes through our system, then the question isn't just what they are. The question is, what else is out there, hiding in plain sight, in the interstellar depths, waiting for us to finally notice?